Our second video on simple statistics is on measures of variation or spread. Variation means how spread out a set of data values are away from the mean. So if values are very spread out, it would have a high variation. If they're not very spread out, it would have low variation. The measure that we'll be using the most is standard deviation, and it's just one way to calculate variation of a sample. We have two symbols for standard deviation. We have S if it's the standard deviation of a sample, and we have sigma if it's, so S for a sample, sigma for a population. Just like the mean, the standard deviation can be affected by outliers. And again, the bigger the standard deviation, the more values are spread out away from the mean, and a smaller standard deviation would be values clustered near the mean. So we have two calculations or two equations that we can use. Okay. The first one is the standard equation for sample standard deviation, where standard deviation is, what we're going to do is take the difference between a value of x and the mean. So how far away is one value away from the mean of the data values in that set? We square that. We do that for each value of x and add them all together. We divide that by n minus 1 and then take the square root of the whole thing. Now you'll probably say to yourself, that looks like a lot of work, and yes, I will show you how to use your calculator to do that. A shortcut formula used by your calculator is a little easier to use, easier to plug numbers into, but again, still tedious. So we will focus on using the list function in your calculator and having your calculator do one variable stats to report the standard deviation. Okay, so let's move down the page. We're going to take a look at how you can compare standard deviations from two samples, and then we'll come back and do some calculations in just a minute. So you can take a distribution, so same these distributions we've been looking at in class. So we'll have a normal distribution like this, and another one. I'll draw a little bit differently. And for both of these, the mean, the sample mean, I'll use x bar for the sample mean, is the value in the middle. And the standard deviation is how spread out the values are away from the mean. So if we call this one sample 1, and we'll call this one sample 2, the standard deviation, I'm just going to write ST for standard and DEV for standard deviation, is going to be larger for sample 1 than it is for sample 2. The values for sample 2 are much less spread out. They're all closer to the mean. The values for sample 1 are more spread out and farther away from the mean. So that's all standard deviation is. We're going to do something called a Z-score, or standardized value for standard deviation, coming up in just a little bit, that will follow us through all kinds of statistical tests that we're going to do throughout the semester. So just a couple other measures of variation. We have variance, which is the standard deviation squared. Okay. And we have coefficient of variation, which is just another measure of variation. Neither of those we're going to use very often, and we'll go back to that later on when we need it. So I want to move on to the next page. Okay. So on this page we have space to calculate the standard deviation using the equations that were provided on the previous page. Okay. So let's make it bigger, move it over. Okay. So you can see that the equation, again, doesn't all show up right here. But what we would have is the sum of x minus x bar, the mean, squared, divided by n minus 1, and then take the square root of all that. So what we would need to do for each value of x, so these are all x's, all the numbers in this list. So we calculated the mean for this data set earlier, and the mean was 1.888, I'll just write 1.89 kilograms. And we know that n is 18. There's 18 values in this data set. Okay. So we have all the numbers we need to plug into the standard deviation equation. Now I'm just going to show you what this would look like if we did it this way, and then remind you that we're not going to do it this way. So the first value for x is 11. We want to subtract the mean, 1.89, and square that. And then we would do that for the next value of x, which would be 3 minus 1.89 squared. And it would keep going, 0 minus 1.89 squared. And then, that's right, and so on, until you get down to the last one, which would be 2 minus 1.89 squared. And then we'd add all those together. Okay. So you get over here, if we were to actually do some of that, we would have, this value would give you 82.99, 1.23, 3.57, and so on, and get to the bottom, and we'd have 0.01 for the last one. And if you were to actually do that and add them all together, you would get 279.74. Okay, so let's write that down somewhere. So that's the top part of the equation. The bottom part is n minus 1. So 279.74 divided by 18 minus 1. And then we take the square root of all of that. And when you calculate that, we should get 4.06 kilograms. So again, very tedious and takes a long time to do. The second equation down here, same idea. It's going to take a while to fill in all the blanks here. So standard deviation is n times the sum of x squared minus the sum of all the x's, and then squared. And the bottom is n times n minus 1. So again, each value of x, and I know we can't see the list anymore. Okay. But the sum of x squared would be 11 squared plus 3 squared plus 0 squared, and so on. And you'd get a value of 344 for that. Sum of x, and then square it, would be 11 plus 3 plus 0. And after you add them all together, then you square it, and for that one, we would get 1156. And now we have the numbers that we need to plug into the standard deviation equation. So n was 18. The sum of the x squared values is 344. The sum of the x's squared is 1156. And we're going to divide that by n, which is 18, times n minus 1, and take the square root of the whole thing. And again, you'd have to plug that into your calculator carefully and in the right order, but if you did, you would get 4.06 again. And that's our standard deviation. So let's take a look at how to do that with your calculator to save some time. And So we have our TI-83 here. Now, I already entered the list in the stat menu before, so we go to stat and edit, and you can see the list is there from when we calculated the mean. We're going to use the same function to find the standard deviation, so we're going to go to stat and calculate, and it's one variable stat, so you just hit enter. And again, if you use list 1, you don't have to tell it it's in list 1, but if you want to tell it what list, you just hit second, and then the list numbers, which are above the numbers 1 through 6. So L1 is number 1, and hit enter. And now you can see we calculated the mean before, but now we have the standard deviation, and we have the sample standard deviation, which is S, and the population standard deviation, which is sigma. Your calculator gives you both, and you can see they're different numbers. Unless you put an entire population of data into your calculator, you should not use the sigma value. Almost always you'll be putting in a sample, so you should use the sample value, the S. So you can see it's 4.056, which if you round it, it's 4.06, which is the value that we got before. Okay, so calculator, much easier than going through all those calculations. Right. One more page for measures of variation. And again, let me make this bigger. Okay. We have something called the empirical rule, where it says 68% of data are within 1 standard deviation of the mean, 95% are within 2 standard deviations, and 99.7 is within 3 standard deviations. So let's draw a distribution. Our x-axis. Draw this as good as I can. Okay, so there's our normal distribution, and we know that the mean is right in the middle. I'm going to use x bar for the sample mean. Okay. And typically, since almost all the data is within 3 standard deviations of the mean, we can count off equally spaced standard deviations going out this way 3 times and going over the other way 3 times. Okay. So this tick mark right here would be the mean plus 1 standard deviation. This would be the mean plus 2 standard deviations. And then we have the mean plus 3 standard deviations. And there's just a little tail left over here. Okay. And then going back the other way, we have the mean minus 1 standard deviation, the mean minus 2 standard deviations, and the mean minus 3 standard deviations. And then again, just a little tail left coming out over here. So the empirical rule tells us that 68% of the data are within 1 standard deviation of the mean. So 1 standard deviation below and 1 standard deviation above. So I'm just going to draw some little lines going up here. Okay. And 68% of our data values are within that range. Okay. 95% are within 2 standard deviations. So between these two lines, we have 95% of all the data in that sample. And then out to 3 standard deviations, above and below, 99.7 of the values fall between those two. And that's the empirical rule. Now, in the next unit, we're going to start talking about probabilities of things. And these percentages are going to correspond to probabilities of seeing a certain value in a data set, depending on what the mean and standard deviation are. So we're just going to introduce that quick right here with something called the Z-score. A Z-score is a standardized value for a number of standard deviations away from the mean. So let me just draw a quick new picture. So instead of a distribution with the mean in the middle and going up 1 standard deviation at a time, both directions. In the Z system, we're going to standardize it so that 0 is the mean, and then standard deviations can just count up 1, 2, 3, and down the other way, -1, -2, -3. So now this value, the x-axis, is actually values for Z, a standardized value. So the calculation for a Z-score, we have Z equals a value for x minus the mean divided by the standard deviation. If we were to do it for a population, we'd just have to put our population symbols in instead of sample symbols. So then it would be x minus mu, which is the population mean, divided by sigma, which is the population standard deviation. Ordinary values are within 2 standard deviations of the mean, and when you convert it to a Z-score, each standard deviation is just 1 value away. So 2 above would be, and 2 below give you a range between -2 and 2. And again, 95% of the data are going to fall within 2 standard deviations of the mean, and in the standardized scale for Z, that's between -2 and 2. Okay. Unusual values would be outside that range, so anything less than -2 and anything greater than +2. If you have a data value that's lower than the mean, it gives you a negative Z-score. Okay. Just like the scale over here, it goes -1, -2, -3 below the 0. Okay. And then the positive Z-score is anything above the mean. So we're going to calculate a Z-score for a weight gain of 6.8 kilograms. Okay. So we have Z equals the kilograms that give you 6.8, that's a value of x, that's an observation. The mean that we previously calculated was 1.89. And the standard deviation we previously calculated was 4.06. And if you plug all that into your calculator, you get a value of, that's not correct. Okay. Let's grab our calculator. Clear that. Okay, so we have 6.8 minus 1.89 and divide that by standard deviation, and we get a value of 1.21. So our Z-score is 1.21. So the question is underneath, is a weight gain of 15 pounds, what would be termed the freshman 15, if you've heard that phrase before, is that unusual? So unusual Z-scores are less than -2 or greater than 2. So 1.21 is actually ordinary. It's not unusual. So we can say no, it is within 2 standard deviations of the mean. So not unusual at all. And that is the end of measures of variation. The third video in this little series will be relative standing and box plots.